In a similar way that electrons have magnetic dipole moments, actually two types of magnetic dipole moments, one coming from the electron spin and the second one coming from the orbital quantum number, protons and neutrons also have their own magnetic dipole moment. Now, before we discuss the magnetic dipole moment of the proton and the neutron as well as the nucleus as a whole, let's recall how magnetic dipole moment is actually created. So a positive or a negative electric current moving in a circular pathway creates a magnetic dipole moment mu that depends on two things. It depends on the quantity of electric current I that is moving in the circular current loop, and it also depends on the area A that is enclosed by this current loop. And if we take the sum of these two quantities I and A, that gives us the magnitude of our magnetic dipole moment mu. Now, mu points perpendicular with respect to the area enclosed by our loop. So in this case, if the loop is my hand, then our mu points upward perpendicular with respect to this surface, with respect to this area. Now, if our current was negative, the mu would reverse and point downward. It would still point along the same axis, along this axis, but it would reverse directions. Now, if we treat the proton as a spherical particle that is rotating about some axis, as it rotates, it carries a certain positive charge given by 1.6 times 10 to the negative 19 coulombs. Now, we can imagine that the proton as a whole basically consists of infinitely many current loops as shown in the following diagram. And each one of these current loops creates a magnetic dipole moment, and if we take the sum of all the magnetic dipole moments of all these current loops, that will basically create the magnetic dipole moment of this entire proton as a whole. Now, of course, this type of thinking isn't actually exactly right, and that's because in quantum mechanics we know the protons aren't exactly spherical particles, they can also act as waves. And so even though this type of thinking isn't exactly right, it's nonetheless very useful to think of it this way to actually visualize how the magnetic dipole moment of the proton is actually induced. Now, protons aren't the only nucleons that can induce a magnetic dipole moment. Neutrons also create a magnetic dipole moment, and that's interesting because we know neutrons as a whole don't actually have a net charge. So this means that although the neutrons have a net charge of 0, they must be composed of some type of constituents, and those constituents themselves must have some type of charge. And these constituents, as we'll discuss in a future lecture, are known as quarks. Now, in the same way that we used a constant known as the Bohr magneton to express the magnetic dipole moment of electrons, we typically express the magnetic dipole moments of individual protons and neutrons using the Bohr magneton. Except for the nuclear case, the Bohr magneton is defined in terms of the mass of the proton. So the Bohr magneton UN is equal to the product of the charge on our proton E multiplied by the reduced Planck's constant h bar divided by 2 multiplied by the mass on one proton. So this is known as the Bohr magneton for nuclear magnetic dipole moments. Now, individual protons and individual neutrons can create a magnetic dipole moment, and equation 2 gives us the magnetic dipole moment mu as a result of one proton, and equation 3 gives us the magnetic dipole moment mu as a result of a single neutron. So 2.7928 times the Bohr magneton gives us the magnetic dipole moment of an individual proton, and negative 1.9135 multiplied by the Bohr magneton gives us the magnetic dipole moment as a result of the motion of our neutron. Now, recall in our discussion of an electron has two types of angular momenta. One angular momenta comes from the electron spin, and the second angular momenta comes from the orbital quantum number. And together, if we sum up these two types of angular momenta, that will give us, this combination will give us the total angular momentum of our electron. However, in the case of the nuclei of atoms, the entire nucleus of our atom only has one type of angular momentum. And so we define the total angular momentum of a nuclei analogous to the total angular momentum of that electron using a term known as the nuclear spin, given by mi. Now, in the same way that the total angular momentum of an electron is given by the total angular momentum quantum number of the electron, the total angular momentum of the nucleus, known as the nuclear spin, is given by a quantum number we call the nuclear spin quantum number, given by uppercase I. And this is defined using this equation. The nuclear spin mi is equal to the product of h bar and the square root of I multiplied by I plus 1, where I is the nuclear spin quantum number I, and this is the nuclear spin. Once again, the nuclear spin is analogous to the total angular momentum of our electron, and the total angular momentum of our electron, the quantum number, is analogous to the nuclear spin quantum number. Now, basically, the nuclear spin of our entire nucleus as a whole depends on the nuclear magnetic dipole moment, and the nuclear magnetic dipole moment is a result of the individual magnetic dipole moments of the protons and the neutrons inside the nucleus. So, what exactly is the relationship between the nuclear magnetic dipole moment and the nuclear spin? So, it is given by this equation. So, our nuclear magnetic dipole moment of the entire nucleus as a whole, given by mu, which is chosen to point along the z-axis because our experimental magnetic field that aligns our magnetic dipole moment of the nucleus also points along the z-axis, is equal to the product of G, a constant known as the G factor, multiplied by mu-n, our Bohr magneton, multiplied by mi, where mi is our nuclear spin. So the nuclear spin determines what the nuclear magnetic dipole moment is. And once again, the nuclear magnetic dipole moment is a result of the combination of the magnetic dipole moments of the individual nucleons of the protons and the neutrons found inside our nucleus of the atom.